Welcome to what, our fourth installment of the AI learning series. My name is Carlos Morales. I run the AI team here at Ambiq. And today we're going to talk about heart arrhythmia analysis. What do you do with like one of these ECG sensors, and what kind of signal can you pull from it? But let me introduce Dr. Adam Page. Adam joined us a couple of months ago at Ambiq, 3 months ago. So much fun we lose track. He has a fairly recent doctorate, 2016, from the University of Maryland, and get this, it's AI in embedded systems, which is like kind of what we do. So perfectly suited to the kind of work we do here. He has over 10 years of software engineering and AI experience, has numerous publications, including some papers and other publications. And if I recall correctly, analysis of heart arrhythmias was part of his graduate work. So this is extremely well suited to Dr. Page's background.
First, I'm just going to give a little bit of context just to get up to speed with arrhythmias, the different ways they can manifest themselves, just some background on the ways we can do sensing with that, and then kind of from there take it into the actual application of detecting AFib. So as most people probably know, heart arrhythmia is defined as like a regular heartbeat. Usually it's the result of faulty electrical signals that typically coordinate the heart's beats in a specific rhythm. I kind of bucket this into like three major categories. These are not like kind of defined, but I kind of like to bucket this way. We can look at the actual heart rate, right? Is it beating too slow? Is it beating too fast? Is it bradycardia, tachycardia, or is it normal sinus rhythm? We can actually look at like a window of your heart rate, your ECG, and we can look for signs for like atrial fibrillation and atrial flutter. And then we can actually look at the individual beats themselves, and that's where we can look for things that are like either premature beats or escape ones, and they can happen in various parts within the heart. And there's a lot of there that I've included, and I'll kind of briefly go over that later. So three main categories. In terms of sensing, I'll say like the de facto is to use like a 12-lead ECG. That's usually how they do it for clinical diagnosis for arrhythmia. And for 12 lead, that actually corresponds to having 12 electrodes placed, and they're making differential measurements. Usually it's from various locations around the heart. And what you're looking for is the heart's beating. It's actually, as it goes through the atrials and into the ventricles, there's depolarization that's occurring. So you can actually look at that propagation, you can measure it. And so you get that kind of, usually what you'll see is that QRS complex that people are familiar seeing. And then another method for looking at arrhythmias, which is kind of new, is using PPG, so photoplethysmography. And that is usually it's done either on the wrist or the finger. It can also be done on the earlobe. It's essentially using LEDs, either green or infrared, and then using a photodiode to look how much, to look at the change in the amount of transmitted reflected light. And that can give you basically an indication of your heart rhythm. And then something else that's kind of cool is like, and that's look into the future, is like data fusion. You can actually use a combination of ECG with PPG, and that can give you such things as the pulse transmit time. And that can be also a very good indicator for looking for abnormalities. So just, I'm not going to go too much in detail. Obviously, I think most people maybe have seen like a QRS complex before. There's various segments, and it kind of coordinates to, so like when your heart's beating, there's like a cardiac cycle. The conduction follows a pretty well-defined path that it takes. I'm going to kind of break it into three parts. You have your atrium, you have your junction, and you have your ventricles. So when your heart is first going to start its cardiac cycle, your SA node is going to fire. That's up in the atrium. That propagates down to the AV node, which kind of does like a propagation delay. It gives enough time for the atriums to completely contract. From the AV node, it then travels down your through the bundle of His, through your left and right bundle branch blocks, and that goes through your Purkinje fibers. And that all of that sequence happens. You can then look at somebody's ECG, and you can identify which portion is currently firing and like where that signal is propagated through. So for example, like the P is going to correspond to that beginning SA node region. The QRS is going to be your biggest one because those are your ventricles, which has the majority of the conduction that happens. So those are like the three major stages. You got your atrium, you got your junction, and you got your ventricles. So usually for your cardiac cycle, there's a pretty well-defined timing. Obviously, it depends on your age, your health, you know, how fit you are. But typically for like the PR interval, you know, is a pretty well-defined. It should be between 120 to 200 milliseconds. Your QRS complex usually is less than 120 milliseconds. And then you actually have your RR interval. That's kind of like corresponds to your heart rate. So depending on how much you're, you know, fatigued or how much you're working out, that's going to vary depending on what you're doing. And so then from there, we typically say when you're at rest, you're going to have you know, your heart rate can either be too slow, bradycardia, which is like defined as less than 60 beats per minute. It can be too fast, which is over 100, or it can be normal sinus, is between 60 and 100. So that was kind of looking at heart rates. So then we can also kind of look at the actual rhythm itself. So in terms of the arrhythmias, you can see here, the two most like kind of common ones you'll see would be like atrial flutter. And the way to think of that is if you're like up in the atrium, whenever that's like discharging a signal, depolarizing, there's almost like a reentrant circuit, and that basically causes it to fire multiple times before it gets to the junction and then gets to your ventricles. And so you can kind of see down here, like in the, I'm not sure how well you can see it. You can kind of see like instead of just one P wave, there's like multiple, and sometimes they'll be referred to as F waves. They can be more sawtooth looking in nature. And then you can actually see like, so something I didn't mention before is your atrium, your junction, and your ventricles, they all act as pacemakers, right? So each one of them wants to basically fire at a defined like period. And usually your atrium with your SA node is the one that's going to be beating the most, and it therefore causes the other ones to not fire. If your SA node, your atrium is not firing fast enough, the other ones kind of act almost like, for hardware people, it's kind of like a watchdog. If it doesn't wake it up and tell it that it's still doing stuff, they're going to go off and do something. They're going to fire themselves. So there's atrial flutter. Again, it's like a reentrant circuit, so you're going to see multiple P waves that kind of refer to as F waves. And then the other side of it is like atrial fibrillation. So this one, it's much more chaotic in nature. You have random depolarizations that are occurring in the atrium. It's usually happening at between 400 and 600 beats per minute. And that's usually out of sync from your ventricles. So they'll be beating slower at 100 to 200. Again, they have their own pacemakers. Because atrium's firing so fast, the AV node can't repolarize fast enough, so it can be in a refractory period where it's waiting before it can depolarize again. So for AFib, you'll see varying R intervals. You'll also see these fibrillatory waves. They can be seen on the ECG, but it's not always the case, right? These are very small amounts of like millivolts that you're seeing, and depending on where the electrode's placed, is it wet, is it dry electrodes, you may or may not actually see those F waves. And then the third category is like for beat. So that's looking at individual, you know, QRS complexes. And you can kind of like break it down, like I mentioned before. You've got your atrial, your junction, and your ventricles. Within each one of those, you can have it defined as like premature, or you can have it as an escape. And they're kind of like self-explanatory. So premature just means when you're looking at the R interval, right, what their normal heart rate is, there'll be a preemptive beat that shouldn't really be there. And that can happen. It can happen in any one of those stages, right? It can happen up the atrium, down the junction, down the ventricles. Or you could have where if your heartbeat is beating too slow, because they're pacemakers, they may have like an escape beat, right? So you'll see like a pause, and then like an eventually you'll see a QRS complex. So for the atrial, they're not as easy to always see. So the QRS is actually still narrow, and it's still less than 120 milliseconds. You can't actually look at the QRS complex itself. There's a slight nuance with that when you have like an aberrated occurrence, which is like can happen in the bundle branches. And then for the junction and the ventricles, usually again, because they're in pacemakers, if your atrium isn't firing fast enough at the SA node, they can actually fire themselves. And what you'll see is in a ventricle, because it's not firing down the junction through that high speed, like basically like a high-speed highway, you'll see a wider QRS complex. And you'll also see like there'll be a pause after it. So in this diagram to the right, this is actually a premature ventricular contraction. And on the left, this is an example of a premature atrial contraction. I should have labels on this. And the way you can kind of see that is here you see like it's abnormal. So you can kind of see that the normal rhythm should be like every like 4 many of these grids. It happened premature, and you can actually see, there's like the P wave looks different. And then for the ventricular one, you basically have that there's no P wave at all. It just goes straight into a QRS complex. So this guy that you see before is actually the T wave that happens after the QRS from the previous one. And then just to branch off, you can actually, so when it's traveling down your junction, it goes after the bundle of His, it goes through like the left and right bundle branch to go to left and right ventricles. So if there's a block there, it can actually cause the QRS to look different. So if it depends on if it's a left bundle or if it's a right bundle. So like a left bundle, you'll actually see like a wider QRS complex. And in the right one, again, you'll see it wide, but you actually won't have like a QRS. So it could be like a QRSR, where you basically can see the difference of when it's going into left ventricles and the right. And that can like look almost like it's bunny ears in the QRS. So hopefully that was some good context on just the different kinds of arrhythmias. For this particular AI application, we are focused specifically just on AFib, atrial fibrillation. And then we're looking at this in a deployed like ambulatory setting where we're using just a single electrode for classification. I'm not going to go through like all the exhaustive different options you have that are like more conventional, but a lot of health equipment that does exist today, like in medical equipment, usually looking at heart rate variability. So they are able to like usually in a controlled environment using 12 leads that are like well placed, they can extract all the QRS complexes. They'll measure all the R intervals and then look at the R variation, right? And there's naturally in a person you'll have some variation. You actually have more variation at night than in daytime. But they look at that and they can actually identify certain kinds of arrhythmias, AFib being one. And what's an interesting thing is if you can extract the R intervals and you plot them against each other. So you plot the current R interval with the previous one. You can create like a Poincare graph, which is good for like modeling chaotic systems. And so AFib, because it's kind of sporadic, it kind of looks like it's like a uniform kind of distribution. So that very far right picture, you kind of see it's kind of spread all over the place. The downfall to this is you usually requires lots of data. You normally have to have a patient hooked up for quite a bit of time. It needs to be very low noise. Otherwise, you're going to pick up artifacts and identify them as QRS, and it can be misleading. So in a kind of a wearable application, you can't really rely on this because you can't have a patient with an ECG, holding their finger on it for several minutes. So for this approach, we wanted to use AI. And there's different approaches. I did do like preliminary studies looking at spectrograms, like using Fourier transforms and bucketing and looking at the spectral energy. Also looked at using some wavelets. For the most part, you usually find it's a trade-off having frequency resolution versus temporal resolution. I didn't get great results with either of these, especially when you're doing it when you train on one set of patients and then test on a complete different set. They kind of struggled. So I thought it'll be much more interesting. What if we just feed in the raw ECG data into a 1D convolutional neural network and let it figure out the best filters to figure out how much temporal and frequency information it wants to retrieve. So for this, what we basically have is it's a 1-lead ECG signal coming in. We're using 5 seconds, and I'll talk about the reason for that later. We do a little bit of pre-processing, so we use a bandpass Butterworth filter between 0.5 to 30 hertz to get rid of noise. We also then, for that given window, we're standardizing it, so we're removing the mean and dividing by the standard deviation. And then we pass that through a 1D CNN, and it's kind of a derivation of the ResNet. Usually ResNets are used for 2D for like images. So I repurposed it and made it for like 1D CNNs. And then one other big change I made is typically for 2D CNNs, the filter sizes are quite small, like 3 by 3. So I expanded that to like 7 or like 11 filters. And in this case, for predictions, we're simply looking to see if it's either normal or if it's AFib. In terms of data set, there's a number out there. I decided to go for the biggest data set I could find that had the most amount of noise and what you expect to see in the real world. So this one, it's called the Essentia data set because that's the kind of the hospital that kind of put the data set together. So these were patients who are wearing a chest-mounted single lead probe, and they're wearing this for up to 2 weeks. So there's like tons of noise in this, right? You can expect as a person's going through the day, showering, getting changed, going for like a jog. All of this is kind of included in this data set. In total, there's 11,000 patients. There's roughly about 58 hours per patient. So they didn't release all of the data, only 58 hours per patient. Of that, there's like 2 billion labeled beats. And these are done by like clinicians. And there's over 17 million labeled segments. So saying if it's like AFib, is this atrial flutter, or is this normal? And I think something that was interesting is when you look at the beat classification, so over 2 billion are identified as normal, but over like 600 million are unclassifiable, right? That's 25% of them are unclassifiable. And that just shows you the extent of how much noise and other artifacts are in this data set that even for like clinician, they can't even discern, what kind of beat it is. And then just quickly going back to the window size. So I went with 5 seconds. When I basically did like a histogram looking at the onset, how long do the AFib segments last for? They can last for a very long time, up to like 40 minutes, sometimes even longer. But usually there's a peak, it's around like 6 seconds. That's where you see the majority of the AFib. That's how long they last for. So I went with 5 seconds. That way I'm not like removing and getting rid of a bunch of useful data. So it's a bit of a trade-off, right? A longer window means you're going to be able to potentially, there's more current chance to actually see some AFib artifacts within the data, but you're also requiring then like the patient or the user to be like holding their finger or like recording for that much longer. And you also lose how much data you have to train on. So in terms of model training, the data set was large. It was over a terabyte. So it was very painful to properly how to like properly train on something that size, especially when there's quite a imbalance between normal and AFib. If you kind of just were randomly sampling, right, you can get over like 90%, I think it's like 95% of the data is normal. So a naive classifier, if you just kind of randomly sampling from the data itself, you're most likely going to be a classifier just going to say, hey, I'm going to always detect that this is normal and I'm getting 95% accuracy. So I had to do some tricks in order to how I like shuffled the data. So one thing I did was like basically use all of the AFib samples. And then for the normal samples, instead of just pulling an equal amount while we're training, we randomly go and we pull different normal samples each time. And this is done like in iterative. So we do it in like batch as we're training the model. It'll basically get a few thousand samples. That's going to be, so much of it's going to be AFib, some of it's going to be normal. And then we update the model and keep training. So for the training size, it was based on 4,000 patients. The validation set was another 1,000 patients, and the test set was 1,000 patients. So one thing that is very important is that we don't want to use the same patient between training and testing because you're usually not necessarily detecting AFib. You're just like memorizing something specific about that patient, right? How they wore it, maybe something that was peculiar about that one patient. So we make sure to separate by patients between the different sets. And then I did do a lot of hyperparameter optimization. So I looked at how much of an impact increased the number of patients. I also looked at the network size, right? So how much data do we need, like the window size, how many number of layers, what widths to use, the filter sizes. And I did find like a sweet spot, right? If you get a model that's too big, it starts to memorize and just the training set, and so it will overfit the data. Too small and it underfits, and it just looks for like trivial things to discern between the cases. And then I did experiment with batch size and shuffle size. And shuffle size was actually something important. The fact that it's a terabyte worth of data, you can't pull that all into memory to train on. So you have to like put them into files. And so you have to make sure if you have 4,000 patients that you're training on, you want to make sure that in your next batch that you're randomly pulling from a variety of different patients and you're getting a good representation of both normal and your AFib. I don't have any good plots for like as it was training. I'll have that as a to-do. But in terms of results, so as I'm iterating over these hyperparameters, you always kind of your use your training set to kind of see how well it's doing and to modify its loss, its weights, and they use the validation set just to kind of figure out at what point is your model like no longer learning, is it overfitting? And this is something you're going to iterate on, right? So indirectly, the validation set, even though you're not training on it, you're constantly looking back as you do different trials and seeing how much better you're doing. So in a way, you're indirectly using your validation set. But for this, we get really, I think, quite impressive scores considering how noisy the data is, especially when you consider that if you look at some of the segments where like the clinician states AFib, there could be a segment of 30 minutes that they said, hey, this atrial fibrillation started here and it ended 30 minutes later. But when you really go in there, there's definitely pockets where the clinician could have probably said this is normal again. In other words, if we were to get 100% accuracy, I'd be kind of concerned because it's probably memorizing what the data set versus really just having something that's going to generalize well. But F-score is a good way to look at how well it's doing, especially on an unbalanced data set. So it's getting 97%. The accuracy is like 96%. And then when we basically use a test set, so this is data I've never like iterated on, it's never seen before. What's interesting to see is the scores are roughly the same. So that's a pretty good indicator this model is going to generalize fairly well. The F-score basically had a delta. It was 0.6% different than the validation set. The accuracy was about 1% different. So it's quite reasonable and quite on par with the validation set. So it's a pretty good indicator that the model has learned weights and it's going to generalize well. And so for model deployment, I'm going to quickly just kind of walk through this. Now that we've trained the model, it's basically in terms of like what it's feeding in, we need to implement a filter. We also need to implement the standardization. So in terms of the sensor itself, I selected it's a MAX 86150. I have some information on the next slide about it. And that basically, it contains both PPG as well as ECG, which is interesting. So that's good for future studies. And then for pre-processing, I implemented both like a Butterworth filter as well as the standardization. And I'm using the CMSys DSP library to basically optimize those for performance. For the model conversion, we're basically using TensorFlow Lite for right now. So I took our TensorFlow model, converted TensorFlow Lite for micro. Using the full model, where we're using 32-bit floating point operations, and the weights are 32-bit, the model size is 537 kilobytes. So it's a bit bigger. And when we quantize this, and that's doing quantization after we've done the training, we can bring that down to 240 kilobytes. So we can get it's not a fourth, but it's like about a half reduction in the size. And then we're also leveraging neural spot to kind of make it easier process to kind of get this thing up and running. So it's dealing with all the I/O for the IOM to do I²C, for optimizing power, and for doing RPC, so that we can basically, as we're pulling the model and deploying it, we can pass it data and actually verify that it's predicting the way we want it to. So just quickly on the sensor selection, it's the MAX 86150. I think it's like 1.8 volt logic, and it includes both a 1-lead ECG and also includes a PPG sensor. And that PPG includes 2 LEDs. It has one that's, I think it's infrared or it's green, and then also has another one for ambient light. So that way it can basically remove that for you automatically. And it's in a fairly small package. It's a bit bigger because it's an optical module. It basically has the optical, like the photodiode, where you can put your finger directly on top of it or your wrist. And then in terms of like its sampling frequency for its ADC, it's 18-bit resolution for the ECG, 19 for the LED, and that could be sampling from 100 to like 1,000 hertz. In terms of doing like an EVB demo, I have the Apollo 4 EVB, and for right now I've had hooked up to, I have from Proto Central has basically a breakout board for that MAX 86150 over like a quick connector. So I have that connected up. I'm successfully able to pull data from it, and I have the model running, and everything's working correctly, except I just need to now like fine tune the model specifically for this sensor, right? So the sensor we're using for this deployment is different than what I trained on, and so I kind of need to calibrate the model so that it's going to perform well on this particular sensor. In terms of future goals, so I do think, so the first one I just mentioned is I need to fine tune the model specifically for the sensor, just kind of calibrate it. Something else I want to do too is actually taking this pre-trained model and fine-tuning it on a slightly different data set entirely. So we have a different distribution, right? It could be different like patient population. That'll be very good for customers, right? Because as they want to fine-tune, if they want to take this model, they're most likely going to want to fine-tune it for their particular application and the sensor that they have. The other thing I think is easy enough to do is to extend the current model to include atrial flutter. And then further on, I do think they'll be very useful to do like data fusion to leverage both PPG and ECG. And something to mention with PPG and ECG is there's actually a few papers out where you can do cuffless blood pressure. So I think that's a popular thing that customers are trying to do, where they're trying to estimate that using those combinations of sensors. So if we can get arrhythmias and we can get like SpO2 measurements, heart rate measurements, and get an approximation of their blood pressure without actually having to wear a cuff, I think that'll be super useful.
Thanks, Adam. That was great. I think it's a great illustration of things that are seemingly simple from the outside can get very deep very quickly. I think this is what's wonderful about AI, right? All the data that it works on is noisy. And writing rules around filtering, you could keep adding filters and doing a spectrogram and looking for specific frequencies and so on. You'll never be able to do that in mass because, everybody's gait is different, everybody's heart is different. This is where AI and machine learning and statistical algorithmic approaches come into play. That's the power of AI.